All right, let's take a look at the homework problems from weeks 1 through 4. We have suppose that a town has 7 bridges, and as pictured below, create a graph that could be used to determine if there is a path that crosses all bridges at once. So, is there a way to go through starting at one point and go through every bridge, but here we missed a bridge. All right, so they just want us to draw the vertices and the edges. Pen marks disappeared. So the vertices and then the edges. So we have a bridge here, we have a bridge here, we have 2 bridges here, we have a bridge here, there's one there, and we have a bridge there. So if we were to draw that on our own, we would have a vertice for island 1, then we have 3 middle islands, and then we have an island at the bottom. And then the edges were the bridges. So that top island could reach any of these islands through their own bridge. And then each of these islands have a bridge to that lower island. But then there was this extra bridge here. So we end up with that extra leg. And the answer was no, that we could not actually make a path and cross all the bridges at once. All right, looking at 3, we have the table below shows approximate driving times in minutes without traffic between 5 cities in the Dallas area. Create a weighted graph representing this data. So we have Fort Worth and Plano. We have Mesquite. We have Arlington. And we have Denton. All right, so Fort Worth to Plano. Fort Worth to Plano is 54. Fort Worth to Mesquite is 52. Fort Worth to Arlington, 19. Probably writing those in the wrong spot. Denton, 42. Okay, so Fort Worth to Mesquite, 52. Fort Worth to Arlington, 19. Fort Worth to Denton, 42. Now we have Plano to Mesquite. Plano to Mesquite, 38. Plano to Arlington, 53. Plano to Denton, 41. We have Mesquite to Arlington, which is 43. Mesquite to Denton is 56. And Arlington to Denton is 50. Okay, so, oh, oops, that's not what I meant to do. I would move this 52 because I can't quite tell what it belongs to now. So replacing that then Fort Worth to Mesquite, I'm gonna call it 52 right here so I can see it better. All right, and number 5, we're asked to find the degree of each vertex in the graph below. So we're just counting the number of edges that are connected to that vertex. Let's double check that. 2, 1, 2, 3, 2, 1, 2, 3, 4, and a 1. In 6, we're also finding the degree of each vertex. We have 1, 1, 2, 3, 4, 2, 3, and 2. Just double checking. Oh, did I go? Okay. In number 8, we're asking which of these graphs are connected. So the only graph here that's connected is the middle one. Otherwise, you cannot reach any other node starting from an arbitrary node. So there's a gap here, and there are gaps here. So there are disconnected networks within the graph. So again, just the middle one. In 11, we have, does each of these graphs have an Euler circuit? If so, find it. So for Euler circuit, we wanted to draw every edge without lifting your pen and without drawing an edge twice. We had a rule that if every vertex was even, then we could have an Euler circuit. So in the first graph, each vertex is even. So we will have an Euler circuit. In the second graph, we have an odd vertex, so there will not be an Euler circuit. And in the third graph, we have an odd vertex, so there will not be an Euler circuit. So we just have to find the Euler circuit in the first image. And you can do that any which way you like. We have 3 more graphs asking if this is an Euler circuit or if these have an Euler circuit. So in the first graph, each vertex is even. Each vertex has a degree of 4. In the second graph, each vertex is even, either with a 2 or a 4 on every vertex. But on the third image, we do have an odd vertex. So we'll have a yes on the first one, a yes on the second one, but a no on the third one. And then we just have to draw our shapes, right? Or our graphs. So you're trying to draw the graph and you're trying to draw every edge once and only once. And you're also trying to not pick up your pen. So we were able to draw the star and then go around the star, and we began and ended at the same spot. Okay, so now for the Triforce that's in the middle, we can definitely draw this shape without lifting our pen because you have to do it in Skyward Soar. Bam! And now berries just popped out of the wall. Okay, now Hamilton circuits. Does each of the graphs have at least one Hamilton circuit? If so, find one. On Hamilton circuits, we'll do a little trial and error. We can, in fact, draw a Hamilton circuit. The Euler circuit wants you to draw every edge. The Hamilton circuit wants you to visit every node. So they have different directives, right? This one is the traveling salesperson problem where we want to start at headquarters, deliver the packages to each person's house, and then return back to headquarters. We don't want to drive down every road. All right, so looking at our second graph here, then I usually just pick a headquarters and then try to draw a path where you can deliver each package and return back to headquarters. But here we get stuck. We have to go back to headquarters, but we haven't actually delivered this package. And the middle image does not have a Hamilton circuit. We always leave one vertex out, no matter what we try. Let's see. And then on our third one, we also have a Hamilton circuit. So we had a yes, a no, and a yes. All right, can a graph have one vertex with odd degree? So every other vertex in the graph has to be even, is what they're saying. Okay, so let's get the pen out. And then it asks, if not, are there other values that are not possible and why? Okay, so can a graph have one vertex that's odd? And the answer is no. Because if you leave a vertex, there has to be another vertex that receives that exit. So you have an exit and an entrance. And now you're in this second vertex. I'm going to label the first one A and the second one B. So right now, A is odd and B is odd. So we have two odd vertices. So we want to make one of them even. So we're going to try to put an exit on B, making it even. But now that exit has to be absorbed somewhere. We can make a new vertex. Now that new vertex is odd. We could have instead tried to go back to A, but then A would now be even. So the nature of the exit requires there to be an entrance on the other side. And so we can have two odd vertices, but we cannot have one. And there's no other values that are restricted in this way. That's the end of the chapter 6 exercises. Chapter 6. Now we'll look at chapter 2. All right. Let's look at chapter 2 exercises. In the first couple, we're just going to make the preference table. So let's look at the A, B, C as the first, second, and third place options. And we have, let's see, 1, 2, 3 votes for A, B, C in that order. And then we have the A, C, B vote choice. And that is there 1, 2, 3 times. We then have the B, A, C vote choice. 1, B, A, C, 1 time. We have the B, C, A 3 times. And the C, A, B twice. That is 12 votes, and there are in fact 12 voters. Let's see. The second one, we have a group of friends that are voting for movies. We have a C, A, B option as their first, second, and third choice. And there are 1, 2, 3 votes for CAB. We have the CBA group, which is 1, 2, 3. We have the BAC group for 2, BAC, BAC. We have the BCA group, BCA, BCA for 2. And then we have that A, B, C voting option. And there were also 2. This sums to 6, or sorry, 6 plus 6, which is 12. And there, in fact, are 12. All right, now let's look at the different styles of voting that we had. So here we have how many voters voted in this election. 9 plus 19 plus 11 is 47. In order to win the majority, if there was close to a tie, you would need more than half the votes. So 23 remainder 1. 23 is half and half. That remainder 1 would make the winner. So 23 plus 1 is 24. Well, that's not a 24. There you go. So 24 for the majority. And then the plurality, because there's three here, if we were trying to decide between a tie, then here we would have 15, remainder 2. And those 2 votes would go to the winner because 15, 15, 15, the two votes there is going to break the tie. So plurality, the minimum would be 17. And on the next question, C, find the winner under plurality. So we've got Buffalo with 9 plus 8. We've got Atlanta with 19. And we've got Chicago with 11. So Atlanta wins in plurality. We can look at the runoff method pretty easily. So for part E, what you do is you cross off the votes of the least voted for candidate, and then you give the votes to their second choice, which is Buffalo. So in the runoff method, 11 go to Buffalo. So Buffalo has the 9 plus 8 plus 11 for 28 versus Atlanta's 19. And now Buffalo wins. So the runoff method has Buffalo as the winner. And then looking at the Borda count method, let me clear this off. What we do with the Borda method is we assign weights, and the least interesting vote for you gets a multiplier of 1. Then from there, you just increase the multiplier by whole numbers, and we have the ability then to put points across the whole board. So Chicago will get 9 votes from this set of individuals, actually, and 18 votes from this set of individuals, and 27 votes from this set of individuals, right? So Buffalo gets 27, Atlanta gets 18, and Chicago gets 9. So in this way, everyone's vote gets counted. And then from there, we've got, let's see, that one's 19. You're right. I'll put that one a little darker, I think. I think the blue is fine. It's just the thickness. Okay, so 19, 38, 57. And then the 11 column, it's 11, 22, 33. And then 8, 16, 24. Oh no, I'm writing with that pen that erases. Okay, sorry about that. Let me redo that. It's like a pen that fills my angst. 11, 22, 33, 8, 16, 24. Okay, check. Now, when we look at Atlanta, Atlanta's getting 18, 57, 11, and 8. So Atlanta has 94 votes. Then when you look at B, you've got Buffalo has 27, 38, 22, and 24. 27, 38, 22, and 24 sums to a total of 111. And then for C, Chicago, we've got 9, 19, 33, and 16. So 9, 19, 33, and 16. That's a total of 77. So we've got part D here for the Boredom method, and it looks like Buffalo wins again. So we've got Buffalo for Borda. Buffalo also won the runoff, and Atlanta won the plurality method. Now, this one was our quiz. So let's take a look at this one. All right, so 8 plus 9 plus 11 plus 7 plus 7 plus 5. That's actually 47, just like our last problem. Make sure my notes are right. And then how many votes for majority? Same sort of thing. 47 divided by 2 is 23, remainder 1. So 23 plus 1. Sorry, for 24 votes for majority. And then plurality, this time, not divide by 3, but divide by 4, because there's 4 candidates. And if there was a 4-way tie, then in this group, each person would get 11. But then there's this leftover 3 votes, and all 3 of those votes are going to go to the winner. That's going to prevent any kind of tie. And we'll have 14 votes for plurality to break a tie. Okay, then who is the winner under plurality? Let's take a look. So we've got 8 for B and 7 for B. So for B, we have a total of 15. Then for A, we have 9 and 7 for 16. For C, we have 5. And for D, we have 11. So under plurality, A has 1. So the answer here is A. All right, let's get this problem. Oh, I resolved. Sorry. A was the winner of the plurality method. Okay, now with the Borda method and the instant runoff method. I think the instant runoff method is easier to do. So I think we should do that one first. So what we do in the instant runoff method is eliminate the last place from plurality. So that means C is out. C being out means that these 5 votes would go to D. So if we do that, then we have A at 16 from part C, B at 15, and then D goes from 11 to 16 in and of itself. Now, if we eliminate D, then we have these 5 votes going to A, and then these 11 votes going to B. So if D's out, these 11 go to B, and these 5 go to A. So now, oh, that's not an A. Trying to think and write and talk all at the same time. So now A is 15 plus 5, and B, oh dang, that was 16 plus 5. 16 plus 5, check, check. B is 15. Get so excited. Okay, 15 plus 11. So we have 21 for A, and we have 26 for B. So in the runoff, looks like B is the winner. So that one was your IRV winner, and that was C, skip D, or E. And now let's look at the Borda method. So for the Borda method, what we have is we have a column with 8, a column with 9, a column with 11, a column with 7, a column with 7, and a column with 5. And for each of our letters, we have a weight in that column. So the form to put the multiplication in a calculator all at once involves adding these products. Okay, so let me get our form out. Oh, try to fill it in right there. Okay, now the Borda method says that we're going to put a multiplier for the choices. And we always start with a 1 on the last choice, and then we go up by whole numbers. So times 1, times 2, times 3, times 4. From there, you can see, at least I like to now fill in the columns, or you could just hunt for your A information or B information. So let's look at the column for 8, right? The last choice is D. The second to last is A. The higher value, C, and the highest value is 4. All right, and then we can do that for all of the columns. So in the 9, B is the lowest, then C, then D, then A. In the next column, A is the last choice, C is the next to last, B, and then D. Your first column of 7, C is in last place, D is in next to last, and then you've got B with the high and A with the highest. Our next column of 7, we have a 1 for D, a 2 for C, a 3 for A, and a 4 for B. And then in our very last column, we have B for 4. Oh, that was 4th place, not 4. So B is 1, valued the least. A is valued second to least. Then D comes in. Then C is the most valued. So in each of the columns in our form here, we have a 1 through 4. So that's a good checking mechanism. Now I'm going to do my own double check. 2, 4, 1, 4, 3, 2, 4, 1, 3, 3, 4, 1, 3, 2, 2, 1, 2, 4, 1, 3, 4, 2, 1, 3. Check, check. When you put this in a calculator, I put this into Wolfram Alpha, and then you just have to change what's in the parentheses for the next entry, which is why I like this form. And the winner of the Borda looks like B. Oh, oh no, it is B. I tricked myself. Okay, so we had B for Borda, B for runoff, and A, if I'm not mistaken, for, yeah, A was plurality. Okie dokie. And I think we have one last problem. It's a Condorcet candidate problem. All right, so in the Condorcet candidate problems, we're trying to compare each candidate to the others. And look at who is preferred most, A or B, when looking at A and B. So in this group of 8, they prefer A. In this group of 7, they prefer B. And in this group of 6, they also prefer B. So it looks like B is the preferred candidate between those two. Now, A and C, we've got in the first group, we have A over C. So 8 prefer A to C. In the second group, C is more preferred than A. So 7 go to C. And then in the last group, 6 prefer C over A. So again, we have 13 to 8, and C is the preferred winner. So right now it looks like A is not preferred. They'd rather have either one than A. But what about B and C, right? What do they look like? Okay, so B to C, B is more preferable to C for these 8 individuals. C is more preferable to B for those 7 individuals. And the last 6 prefer B over C. So here we have 14 versus 7, and B is preferred over C. So when we compared B to C, we got that B was the winner. So B is a Condorcet candidate. All right, see, that's it. I hope you have a nice day, and I will see you on Wednesday. The test is on Friday. So we have a review Wednesday, and we have the exam Friday.